लेग कौन सा होता है लेग?
Hello, this module will be covering network layer functionality and features. The topics covered by this module are the characteristic of network layer, the shape and the role of IPv4 packets and IP version 6 packet. We will be explaining how network devices are using routing table to forward packet to a destination network and the functionality of a routing table in a router. We start with network layer characteristics. A network layer, as we see it previously in OSI reference model, it has multiple roles, and in the TCP/IP model, which is relying on OSI reference model, they kept part of the functionality of an OSI IP network layer in the TCP/IP model. Therefore, the network layer performs four basic operations: addressing and devices, encapsulation for the information or the segments provided by the upper layer, and routing, how to define the path which is going to be used from node to node to reach the destination. And the first one is the encapsulation. In the TCP/IP model, we have IPv4 or IPv6 that are the network layer communication protocol. In previous module, we talked about encapsulation. When it comes to network layer, the segments of data provided by the upper layer will be encapsulated within the data field of an IP packet. IP packet header will be examined by all net layer 3 devices that are being crossed along the path from the source to the destination. The IP address, which is a logical IP address identifying the source endpoint and destination endpoint, does not change from source to destination. Later on, we'll be explaining what do we mean by NAT, which stands for Network Address Translation, and in this case, when deploying NAT functionality within a router, the address will be changed. IP characteristics are, first things, connectionless. It's a connectionless oriented protocol, which means transferring data from source to destination should not require a prior establishment of a connection between the source and destination, similar to the transport layer or some layer 2 protocols. It's a best effort protocol, which means when a packet reaches a certain node, it's going to check its routing table to find a route which would help it to forward the packet to destination through a destination port to reach the next hop which will lead it to the destination, to be delivered to the destination. If within the router there's no enough resources or there's no route within the routing table or any other reason, the packet will be dropped, which means that the router works as a best effort node. Also, IPv4, which lay on the third layer, is not directly connected to the physical layer. It's going to be an intermediate layer, which is data link layer, which is layer 2. So this protocol is media independent. It's independent from the transmission medium, if it's a wireless or wired, or it's a fiber optic or a wireless connectivity or a copper wire. What do we mean by connectionless? IP layer is not going to establish a connection with the destination prior to sending the packet. Also, there is no control information needed, which means synchronization between source and destination, acknowledgement between the source and destination if these packets were received or not. There is no acknowledgement. The destination is going to receive the packet when it arrives, but there is no a pre-notification sent by IP. If a certain application requires a connection-oriented protocol, we rely on the transport layer, which is going to be provided by the TCP protocol as a transport layer. What do we mean by best effort? IP is a best effort protocol, which means that the packets delivered to the destination, there is no guarantee in this delivery, which means if a certain node go down and the intermediate node through the path along the path from source to destination, or there's no resources or no route, the packet will be dropped. There's no buffering of the packet to check if the packet is well received by the destination or no. This will reduce the overhead since there's no mechanism to resend data if the data is not received. Also, it's the IP doesn't provide it's not a reliable protocol, which means if data is dropped for some reason, IP layers will not recover from this loss. There's no acknowledgement measurement used deployed in order to know if the packet is well received to the destination or no. So it doesn't know if the other device at the end is operational and if he received the packets. There's no feedback from the source, from the destination to the source. What do we mean by IP is a media independent? First, IP protocol is unreliable, just explained before in the previous slide, which means that the packet, if it's not received by the destination or if it's received with an error, there's no mechanism to recover from a loss of packet. There's no acknowledgement. It cannot retransmit after an error. There's no realignment out of sequence between of packets. All these three features or functionality, IP rely on other protocols to deploy these functionalities. Also, it's media independent, so it doesn't care about the below transmission medium, either it's a wireless or wired, it's a wired over copper wire or a fiber optic, what type of electrical signal or light or electromagnetic wave is going to transport this data. It doesn't care about it, it doesn't concern. It's not a concern for IP layer. And that's why IP can be sent over any type of media. To identify, the packet when it's conveyed over a link to reach the destination. The capacity of the link, we call it a capacity or a bandwidth. The available bandwidth or the size of the packet has a certain limitation. For instance, if you cross a bridge or a tunnel, there is some limitation for big truck. They cannot pass through a bridge, or sometimes for a certain limitation in weight. Also, there's limitation for some big 6 wheels, they cannot cross a tunnel. The same things for IP network. So to avoid this problem, a network layer is going to identify what we call the maximum transmission unit, or MTU, which is the maximum size of an IP packet that can be transported over a certain path from source to destination. So along the path, if the maximum MTU can be transmitted, cannot be carried by a 6-wheel, so you will not put a packet into a 6-wheel. Other features provided by layer 3 protocol IPv4 is the fragmentation, which means if the IP packet generated by the sender is way far bigger or larger from the MTU, the IPv4 functionality of fragmentation is able to cut this packet into multiple smaller chunks or units that can be transported over the path. Since its MTU is becoming acceptable by this path. IP version 6 support fragmentation, but that does not recommend it. So it's better do not use fragment packets, because if one fragment is lost, all the packet is lost. So, and sometimes the loss of packets is due to congestion, where we have heavy traffic over the link or over the road. If one packet is delayed or it's broken, doesn't reach out to destination, this will cause the retransmission of all the original packet, which is going to be refragmented into multiple fragments, which causes more of congestion since we are putting on the network more and more packets. In this section, we'll be discovering the IP packet format. An IP packet, which is a unit at the layer 3, is made of, it's a PDU, it's made of a header and a payload. The header in the packet IPv4 packet hold the source and destination logical IP address, identifying a host whenever it's business host worldwide connected to the internet backbone. It contains also information usable by the network layer to process this information to be used for delivering data to the destination. So, an IPv4 header has multiple characteristics. First of all, it's a binary. It's in binary. It has several fields of information. It's read from the left to the right. On every row we have 4 bytes. 4 bytes times 5 lines, it's a 20 byte, which is the fixed header of an IPv4 packet. It can carry an optional field in the header, which increases the header size into multiple more bytes, which should be a multiple of 4. Okay, so what's going to carry? In the first line we have the version over 4 bits, which indicate which is version this IPv4. It's a v4 or v5 or v3 or v2. The most stable one, it was v4. So it passed through v1, v2, v3, and until it is v4, which was a stable version. Then they enhanced v4 with v5, but still it has some missing features, then they pass to version 6. Then we have another 4 bits which indicate the header length. Honey, in this field, if we can see if we have an optional field in the header, which means this value doesn't indicate that we have 20 bytes in the header. It's more than 20 bytes, which means that we have a multiple of 4 bytes, which indicate that we have an option field used in the IPv4 header. Then it comes 1 byte, which is differentiated services, stands for differentiated services. Before it was a type of service which identifies the quality of service required to be by this packet to be processed. Here we can have different indication about the quality of service related to the type of media carried within this IP packet, which means if this IP packet is carrying real-time data coming from a voice over IP call or a network game, which means real-time application, it has different quality of service requirement than if we are using non-real-time application such email, surfing the web, chat. Then we have a total length field running over 2 bytes, which indicate the total length of, which means we have the header, fixed header and variable header if available, and we have the size of the payload field. So to know the size of your payload field, which should be encapsulated from the IP packet to be delivered to the upper layer at the receiver side, we make total length minus header length, and we can get the packet payload size. Then we have 3 fields in the identification in the second line, which means an ID for every packet generated. Then we have 2 fields, flag and fragment offset. These 2 fields are used when we do fragmentation. So the fragment offset indicate the which part from the original IP package is carried within this fragment, and the flag if there is more fragment following, which will indicate either there is more coming with a bit m equal to 1, or it's the last fragment and it will be equal to 0. Since this IP packet is carrying the IP source address and destination IP address of the source and destination to be reached, the final destination, so the intermediate node need to route this packet from node to reach the destination, and before this router, this intermediate node should define the path to be used from to reach destination coming from the source. So sometimes while running on the network, a destination couldn't be reached. Okay, so the packet will be keeping running on the network. So to avoid having this type of packets coming from nowhere and going to nowhere, they defined what we call a time to live, which is indicate whenever it's a counter decremented every time you pass through a router, an intermediate node, until it reaches value of equal to 1 or equal to 0 equal to 1, which means the last router before cannot receiving this packet with TTL equal to 1 will not be able to forward it to next hop لأنه بس وصله he has to decrement to 1, it will be 0, so it will not be routable anymore, it's going to be dropped. This is the purpose of time to live. Protocol field indicate which upper layer is using the services of IPv4 packet. For instance, if it's a TCP, in this field, in the protocol field, we'll be having a certain value indicating that it's TCP protocol, like value equal to 6. If it's an ICMP protocol, it will be value of 1. If it's UDP, it will be equal to 17, and so on. The last field we'll explain is header checksum, which is like the FCS within the Ethernet frame. Is calculated over a pseudo-random header to check if there is an error in the pseudo-random header. The IP, I missed something, that the source IP address and destination IP address are over 32 bits, represented in dotted decimal value. In this video, you will be watching a sample of IP headers using Wireshark, which is a tool to sniff, to capture traffic over the wire and to analyze it, very used by security officers. In this section, we will be understanding the IP version 6 packets. In the previous version, in the IPv4, there was 3 major limitations. The first one, the size of the number of available IPv4 addresses. Since the boom now is to have everything connected to the internet, we reach a time where we have a lack of available public IP addresses. So they had to find a solution. Another one, it's a lack of end-to-end connectivity, which means to make IPv4 survive, they have to, in the IP address schema, there was a public IP addresses which were going to be used by every host connected to the internet to be reachable over the internet, but still we have some pool of IP addresses called private IP addresses. They are used locally and they are not routable over the internet backbone. So they identify a solution, which is the NAT, network address translation, where we use the private IP address, which is not routable over the internet, or are not reachable over the internet locally, so it can be reused by multiple companies. But whenever any host needs to reach out to the internet backbone, he has to get a public IP address. Since it's not a temporary solution, it also it creates issues on the network while manipulating the network address and address. So because we have to move from a private IP address to public IP address to be delivered to this destination, transform it into private IP address to find finally the host on the local network, and while replying back we have to have the same process. It increases the latency and we still have some troubleshooting issues. So the role of IPv6 is to recover from all this limitation and provide more enhancement. IP version 6 has been developed by the IETF. It overcomes the limitation of IP version 6. First of all, they increase the address space from 32 bits up to 128 bits, which increases the number of available IP addresses. Improved packet handling while simplifying the header. And finally, eliminates the need for NAT, since there's a huge amount of address, so no need to use private IP address internally and map it to a public IP address. What are the main changements in an IP header? They kept the version, the quality of service or type of service of differentiated services is still usable. They call traffic class. Here, instead of using an identification of every packet, we use a flow label, which can be used to identify a flow of packet generated by a certain source going to a certain destination. Since instead of making total lengths minus header lengths to get the packet size, they eliminate these two fields and replace it with payload lengths. The next header, similar to the option field within IPv4. Here we can use the features available whenever it's required by an IP packet, depending on the requirements of the upper layer protocol. And hop limits is the TTL, time to live. And the IP address source and destination, each one it spans over 128 bit. We minimize the number of fields, but we increase the size of the IP headers to reach 40 byte instead of 20 byte. So since we don't need fragmentation, the fragment offset are eliminated, and since it's a best effort protocol, which means even if we discover there is an error in the header, so no actions will be taken, so we removed the header checksum. So just a few words about the extension headers, which provide optional network layer information. They are optional and they are placed between the IPv6 header and the payload. It might be used for fragmentation, for security, for mobility support, etc. But it's recommended, even if the fragmentation is defined within the RFC, within this protocol document, but it's not recommended to do fragmentation with IPv6. This video can show you also IPv6 headers in Wireshark encapsulated within Ethernet packets. What are the control information and difference between packets? In this section, we'll be discovering how a host is going to route this packet to reach the destination. Let's consider this following topology. We have two PCs connected to a LAN through a router, which need to connect through a WAN, which is the cloud, to a remote host. These two local hosts, PC1 and PC2, they both have the same address. Let's talk a little bit about addresses. You know, every one of you has its own a unique identifier. Every one of us has a unique identifier, which is our name and surname. Sometimes you can find two hosts having the same name and surname, but we still have some difference, which is the dad name, and more we have the name of our mother. So within a certain family, in your family, you all are having the same surname, but each one of you has a different all of us, we have the same family name, but we have different name. Okay, so an IP address, it's similar to a person identification, which means it has a family name and a name. The combination of these two we call a host name. Okay, so every user has to have a unique IP address identifying its host. So PC1 in this case, on the local LAN we have the family name, which is 192.168.10 over 24.0.24. The last byte .0 can, since it's 24, which means 24 bytes, the first 3 bytes are used for the family name, and the last byte is used to identify the name of every host. On this LAN. Okay, so we have here 3 hosts. We have the PC1, PC2, and we have the router with the interface connected to this LAN. A switch, it's called a DCE, running over layers 2, is not going to be identified by an IP address unless it's used for the management of the switch. So based on these IP addresses, every host, including the router and the remote host, is going to create its own routing table. So the host can send packets to a local IP address, what we call a local host IP address, أو بسموها local loop. For the IPv4, it's 127.0.0.1. For the IP version 6, it's 127 bits to 0 and the last bit equal to 1. What do we mean by local host? Local host, which means destinations that are on the same LAN, and the remote hosts are devices outside the same LAN. How a host is going to forward a packet? Either it's going to keep it locally or it's going to transmit it over a remote host. So the method of determination is the following. For the IPv4, every source uses its own IP address and subnet and the destination IP address to check if they are both on the same LAN or different or a remote LAN, which means that if both of them they carry the same family name, which call it a network address, then these two hosts are members of the same LAN. If these two hosts are having different family name, we call it a network ID, a network address, then these two hosts are running on different LAN. For the IP version 6, the source uses the network address and the prefix advertised by the local router to check if this host is member of his LAN or no. So any traffic locally is going to be transmitted locally from PC1 to PC2 if PC1 send data to PC2 using the IP host address of PC1 as a source and IP destination address of PC2 as a destination address. If PC1 need to communicate with a remote host outside the network, then the packet is going to be forwarded over the default gateway, which is the router in this case. What do we mean by default gateway? A default gateway, it's a router or a layer 3 switches acting as a router, okay, with some features. They are the router on the LAN interface, it should have the same IP address range, which means the same network address as the host. It can accept data from any host running on the LAN and is capable of forwarding traffic of the LAN. It can route to other networks. If a device doesn't have a default gateway or it has a bad default gateway, then traffic will not be available to be leave the LAN and it will be dropped whenever it reaches the router. Let's suppose we have the following topology. We have PC1 and PC2, which is similar to the previous topology, connected to a router through a switch, which makes the local LAN, and every host is directly connected to this local network, so they are part of the network 192.168.10.0/24, where PC1 it has 192.168.10.0 as a network address, and it has as an IP address which identifies PC1, it's 192.168.10.10, while PC2 will have 192.168.10.15, and the local interface of the router will have 192.168.10.1 as an IP address. So the host will know the default gateway. You configure the PC1 with a default gateway, which means any destination address that doesn't fit within its own routing table is going to forward it to the default gateway. Usually, a default gateway is the router on the border of the network. How it's going to learn this default gateway address? Either statically it's going to be configured on the device, or it's learned through a dynamic host configuration protocol, which is called DHCP when running IPv4. If it's running IP version 6, so the default gateway is sends the default gateway through a router solicitation packet, or can be also configured manually. A default gateway, we call it, is the last resort route in the routing table. Let's check host routing table. If you look at this table, it has by typing the command line interface CMD from your device, you will type netstat space -r, and you will get the IPv4 routing table, which has multiple fields, multiple columns. Where first column is the hardware destination, which means, or network destination, which means we identify only the family name, which is the net ID, within the routing table. We cannot populate a routing table with all host IP addresses, otherwise we're having a very huge routing table, which will increase the process time. So we have the network address to identify which portion of the IP of this 32-bit are identifying the net ID, and which portion of these bits are identifying the host ID, which mean the name and the surname, family name. We need to use a net mask, a subnet mask addresses, where this subnet mask is defined as every bit related or used for the net ID is going to be equal to 1, and all bits related to the host ID is going to be equal to 0. يعني let's suppose we have PC1, okay, 192, which has IP address 192.168.10.10. If it's 32-bit, it's a dotted decimal value where every byte it's conferred over every bit, over 8-bit. 8-bit divided by multiplied by 4 equal to 32 bits. Okay. If in this case we reserve the first 3 byte as a family name, or we call it net ID, and the last byte for the host ID, or what we call it name, to identify the host. Okay, so we have 24 bits related to the net ID, and what's kept for the host ID is 8 bits. Okay, so the subnet mask will be 1 1 1 for every byte. Okay, thus the dotted decimal value, the first byte equal to 1, the second one equal to 1, all bits are equal to 1, the last one also equal to 1, before last one, and the last one equal to 0. So here we have all 0, here we have all 1. If we replace it to convert it to decimal value, which means we have 255.255 dot 255 dot 0. Either we can represent the subnet mask as dotted decimal value, or we can represent it as slash with the prefix length. In the routing table of a host, we use a dotted decimal value to represent a subnet mask. Then we have a gateway which indicates the IP address of the router on the border or on the edge of this LAN, which interface we are sending these packets over it, okay, and the metric which represent the cost or to reach this destination. هذا الcost it can be from multiple sources. It can be it's a number of hop. Let's suppose you're going from your house to your destination. Let's suppose university. You count how many roundabout you need to cross before reaching destination, and you use it as a cost. Or you can use it as the capacity, how many car it can run over this path to reach your destination, which is your university. It can be a combination of number of hop, delay, bandwidth, capacity, etc. Okay, depending on the routing protocol. Okay, so we have the interface list, we have the IPv4 routing table, or we can also have the IP version 6 routing table whenever we use netstat dot space minus r. In this section, we'll be introducing routing concept. So far, what we did, every host will be building its own routing table. Usually, it's made with his own IP address running over the interface, the default gateway, and also it might have multiple other IP network or entries within routing table to reach some specific IP host. So usually, whenever you reach a certain destination, which PC2, which is outside of your LAN, if you look at the network addresses, it's 92.168.10.0/24, while on the left, on the right hand of your router R2, there is another LAN, it's 10.1.2.0/24, okay, and also between the two router R1 and R2, there is another WAN connectivity representing the connectivity, the point-to-point connectivity between R1 and R2, which hold also another network ID, network address, which is 209.165.200.224/30. So if we look up at router R1, it has two interfaces, one connected to the LAN through interface G0.0.0/0.0, and it has another interface connected to the second network, okay, one network in here, which is a interface G0/0/1. So let's suppose PC1 need to send a packet to PC2. This IP packet generated by PC1, it holds an IP address source, which is its own IP address. It's 192.168.10.10. Okay, and the IP address destination is the IP address of PC2, which is going to be 10.1.2.10. So when it packets, it passes through the routing table of PC1, he can see there is no specific explicit IP route within his IP routing table to check how to reach PC2, so it will send it to through default gateway entry within routing table. okay, through the LAN. So through the switch it will reach R1. R1, he will check his routing table. By looking up the routing table, he may do a matching between the destination IP address and every entry within the routing table. It's a sequential reading of this routing table. So what he will be doing, he take the IP address, which is a host IP address, while the routing table is carrying only network address. So you do a logical AND between the destination address and the subnet mask to get the network address related to this destination IP address, and he compare it with the value. Is it the same? Here we have 10.1.1.10/24, which means 10.1.1.0/24 is the network address. If you compare it, it's not the same. So he's going to pass to the second entry within his routing table. He's do the same by making a logical AND between the destination address and the subnet mask /30, which means it's 255.255.255.252. Also, he will not get the same network addresses. Here 10.1.1, here is 209, etc. So he will pass to the last IP network address. It is having a matching, okay? So he know that he has to forward this IP packet to router R2 through its interface gigabit.0.0/0/0/1. Okay. هلا if he didn't found any explicit route within his routing table, he can use the default route to send the IP packet to the following network address, router. So how we build an IP, how the router build his routing table? We have multiple entries. We have 3 type of entries. We have the directly connected one, which means the IP address of the interface of the router, it has an IP address. The network address of this IP of this interface will be a directly connected network address within the routing table. So router R1 is member of 2 different network address. Since it has 2 interfaces and every interface is located in different network. So router 1 is directly connected to 192.168.10.0/21 through interface gigabit G0/0/0/0/0 and is directly connected to interface G 209.165.200.24/30 using interface gigabit 0.0/0/0/1. We add to it either an explicit route to identify how to reach 10.1.2.0/24 by indicating it has to go through R2 using interface gigabit 0/0/1, or we can use a default route, which means that any IP address, if you look any IP address with any subnet mask, it's going to be forwarded to the destination address through interface gigabit 0/0/0/1 يعني through router R2. A default route, it has any IP address represented by 0.0.0.0 with any subnet mask also represented by 0.0.0.0. This is your default route. So how we built routing table? Either we built it statically, which means that the administrator of the network has to configure manual route on the router, okay, it's going to be adjusted by the administrator depending on the topology. It's good static routes are configured manually. It should be adjusted by the administrator whenever there is exchange in the topology of the network. It's useful for small network, and it can be usually combined with dynamic routing. So usually the default route is configured as static entry within the routing table. Dynamic routes are automatically learned through protocols deployed between routers to update the information and to keep updated this information, to choose the best path to the destination, and to find new best paths whenever there is a change in the topology. This video will explain the information in the IPv4 routing table. So if you look at the routing table of a Cisco router by checking the show IP route commands on the command line interface, you will get the following information. First of all, you have some codes which indicate the type of uh, the index of every entry within the routing table. It's either directly connected local interface IP address FL, C, which means a directly connected interface, S stand for static routes, O for SPF, and D for EIGRP. You have also R for RIP. So when you do show IP route, it will show types of routes directly connected either C and L. Remote routes learned via a dynamic routing protocol such as SPF, EIGRP, or RIP version 2. And you have your default route is static route identified by S with a star.
قفشتك هذا نسكره ITP IDBG PowerPoint this shit recording is still link record
This module will address
module
the
access
protocol address resolution protocol, or ARP. This module objective is to explain how ARP for IP version 4 and how neighbor discovery for IPv6 works, mainly to compare the roles of MAC addresses and the IP address, to describe the purpose of ARP and the operation of IPv6 neighbor discovery. First section is the role of MAC and IP addresses. In reference to the OSI reference model, the MAC address reside in the layer 2. It's one of the functionality of layer 2, which identify the physical address of a device or an entity. If you are in a local network such as Ethernet network, the physical address, which is a medium access control address, is embedded inside the NIC or network interface card to permit the communication between NIC cards, between two entities on the layer 2. while the layer 3 logical address, which is function of the layer 3 protocol, which identify a logical identity of any device connected to the network, while using the TCP/IP model, it's an IP address. So it will identify the source device IP address and the destination device IP addresses. So the role of a layer 2 address is to deliver frames from layer 2 device to another layer 2 device. Within a local network, it will be between a NIC card to another network interface card, while a destination IP address on the same network will have uh, uh, so how it is related, the MAC address and the IP address. In fact, every device is going to be identified by a logical IP address on the layer 3 and a physical address on the layer 2. So we associate between, there is an association between the physical address and the logical address on the layer 2 and on the layer 3. So to reach a certain destination, we need to know on your device, on the source, we know the MAC address, it's embedded on the network interface card. We know the logical address, it's configured on the layer 3 IP layer. While reaching the destination address, we need to have the destination IP address and the destination MAC address. So if we take the following example where PC1 and PC2, they are both connected to the same switch or to the same Ethernet network, local network. So to be able to reach the destination, okay, the MAC address destination associated with the IP address will be the same configured on the device, on the destination device. In this example, PC1 having a MAC address of AAAAAA, while the IP address is 192.168.10.10. The network address is 192.168.10.0/24, and the PC2 is having a MAC address of 555.555.555, and the IP address is 192.168.10.11. So we can see that PC1 and PC2, they are part of the same network. So when PC1 generate a packet, an IP packet, where the destination is PC2, in the header of an IP packet, it will be configured with a source IP address related to PC1, and the destination IP address will be the IP address of PC2. When this packet is going to be encapsulated within an Ethernet frame, so we have to find to configure the MAC address source of the Ethernet frame with the MAC address related to PC1, while the MAC address destination within the Ethernet frame should be the MAC address of PC2. A MAC address is related to LAN, so mainly to Ethernet protocol, or any layer 2 protocol from the IEEE. So when we need to associate a MAC address to an IP address, it should be located in the same LAN. So if the remote destination is outside the LAN, which means it's really connected to another LAN where the two LAN are interconnected by a WAN network, where here in the example we have a WAN network between R1 and R2, which is a point-to-point link. So to be able to discover the MAC address of the destination, which is PC2 in this case, if PC1 is communicating with PC2, so we have to have some means, some tools, which will help us to discover the MAC address of the destination. Here it comes the role of ARP protocol for IPv4 and ICMP version 6, which is network discovery options of ICMP v6 for the IPv6 protocol. In this lab, you will be identifying a MAC address and an IP address. section will be explaining in detail the ARP protocol, which stands for Address Resolution Protocol. ARP protocol is used to determine the destination MAC address of a local device if you know the IP address destination. So the two basic functionality of ARP is to resolve IPv4 addresses to MAC addresses and to maintain an ARP table of IPv4 to MAC address mapping. So why do we need such protocol? Usually, when you build an Ethernet frame encapsulating an IP address, usually you need to know the IP address of the destination and the IP and the MAC address of the destination. And how you get the IP address? Either through DNS, for instance, okay, or maybe like such Win server, which where you can associate under Windows a name with a domain to an IP address. Okay, so he will resolve by knowing the name. You can get the IP address from the server, DNS server or other server. For the MAC address, to resolve the MAC address of the destination, either you have to go by yourself and check the MAC address configured on the device of your destination, or you need some means to get the MAC address of the destination. This is the role of ARP. In the previous slide, we talked about two functionality of ARP. The first one is to map an IP address to a MAC address destination. The second one is to build and to maintain an ARP table which maintain the association or mapping between an IP address and a MAC address. So to be able to send a frame to a certain destination, first of all, you have to search the ARP table to check if the destination IP address is already within the ARP table. So second step, if the destination IPv4 are on a different network, so the device will search the ARP table for the IPv4 address of the default gateway instead of the destination IPv4 address as per the first point. If the device locates the IPv4 address, so it will get the mapping between this IP address and the MAC address within the ARP table, and then he will be able to add it to the destination MAC address field in the frame. If there is no ARP table is found, then the device he has to execute the ARP protocol by sending an ARP request. This video will cover an ARP request for a certain destination MAC address. In this video, you will see an ARP reply related to an ARP request. In this video, you will see an ARP request transmitted to a host where the destination device is outside the LAN, outside the same network, around the same network. So you will see how you will get the default gateway MAC address instead of the MAC address of the real destination device. How the ARP table is built. Whenever you transmit an ARP request and you receive an ARP reply, the mapping between the MAC address destination and the IP address destination will be generating an entry within the ARP table. But this ARP table is not permanent, so it will be flushed after a certain period of time. The timer of the ARP cache differs from operating system to another operating system, but also it can be removed manually by the administrator, and it can be configured statically to have a permanent entry within the ARP table. The main command used to check the ARP table on a Cisco router is show IP ARP. So you will see that there is an association between the IP address, which here is 992.168.10.1, with the hardware address, which is a MAC address. In this case, it's A0EU0.AFD0D.E140, which represent the MAC address of the gigabit Ethernet interface. To display the ARP table on a Windows 10 PC, you can use the command ARP-A. So you can see the ARP table where there is a mapping between the MAC address destination and the physical MAC address destination associated to this IP address. Either it's if the device is local on the network, you will get the physical address of the device itself, or if the destination IP address is outside the network, you will get the MAC address or the default gateway of the network. In this case, the default gateway is the router on the edge of your network LAN. The main issues of ARP are the ARP broadcasting and ARP spoofing. In fact, when you generate an ARP request, it will be, since you don't know the MAC address destination, it will be encapsulated within an Ethernet frame where the MAC address destination is a broadcast MAC address. Okay, so every device on the LAN will be receiving this ARP request. When you have excessive ARP broadcast, it will cause some reduction in the performance of the network because ARP frames, MAC address destination frames having a destination MAC address which is a broadcast, and every all bits equal to 1. It will cause in the switch itself, it will cause a high process to transmit the frame, to duplicate the frame to all ports within the Ethernet switch. This will cause a slow performance for the unicast frame. It can be also used by a hacker to slow down the performance of the network. So the ARP reply also can be spoofed by a threat actor to generate an ARP poisoning attack. So at the enterprise level switches, you need to, as an administrator, to include mitigation techniques to protect against ARP attacks. In this lab, you will be examining the ARP table. So you will examine an ARP request, you will examine a switch MAC address table, and you will be examining the ARP process in remote communication. In this section, you will be discovering the IP version 6 neighbor discovery protocol, which is really similar in behavior to ARP request for IPv4. This video will explain how the IP version 6 perform address resolution based on the ICMP v6 neighbor solicitation and neighbor advertisement messages. The neighbor discovery protocol provides, in fact, multiple functionalities such as address resolution, router discovery, redirection services, using neighbor solicitation and neighbor advertisement messages for device-to-device messaging such as address resolution. The router solicitation and router advertisement messages are used for messaging between devices and routers for route discovery. And the ICMP v6 redirect messages are used by routers for better next hop selection. How IPv6 neighbor discovery resolve addresses. In fact, PC1 who should communicate to get the MAC address of PC2 will generate an ICMPv6 neighbor solicitation message asking who has this MAC address to send me who has this IPv6 address to send me his own MAC address. So the target destination will reply with an ICMPv6 neighbor advertisement messaging saying that I am this IP address and this is my MAC address. In this lab, you will made of two parts. You will be completing the IPv6 neighbor discovery deployed on a local network and how IPv6 neighbor discovery is implemented over a remote network to resolve the address.
open